Okay, so the next talk is given by Stelios Tsampas on logical predicates and relations are removed, yeah? In higher order mathematical operational semantics.
Yeah, let's address this. I apologize, didn't have time to make the slides on relations, even though the theory arguably works better for relations. That's the one thing I want to say. Second thing I want to say, I'm happy to be back here in Belgium among friends. Third thing, I thank Benedict and Dima for warming up the audience on initial algebra semantics. This is a very important aspect of what you see there, mathematical operational semantics. Of mathematical operational semantics. What mathematical operational semantics is about is the interaction between initial algebras and final coalgebras. And I should add that there has been work, in fact, on operational semantics with initial algebras, and mathematical operational semantics is this limited work that Dima spoke about. And all these things will be hidden, however. Even though you're warmed up, they are part of the framework, but I will not speak like this. I will not, they will be underneath. They will be part of the foundations. In this program of higher order abstract GSOs, we are here today on the work on logical relations and predicates. So let's get right to it. Which of you is familiar with logical relations? How many of you have actually done proofs using logical relations? A little bit, huh? Right? Okay, that's great. All right. So let's first discuss about the setting, the general setting of such proofs, and let's focus on predicates, really. So you are given an operational semantics. We're talking about operational logical relations, if you will. So it's typically a type lambda calculus. We're going to be using this notation for the set of terms. So for open terms, lambda tau of gamma and lambda tau for the set of closed terms. All right. You are then given a type index logical predicate that you want to prove, a program property. Be it strong normalization, type safety, which absolutely, positively cannot be proven just by straightforward induction. All right. So what do? You construct this magical kind of logical predicate which is included in P, so it's like smaller than P, implies P, and it's logical in this sense, right? For any term T and S, that both of them are this logical predicate, and if the suitable type T and the suitable type to apply this, then the result is also in square P. And then proceed by induction to prove that the open extension of square P holds. These look pretty systematic, right? But they are like people who have worked with those logical predicates, they can sense that you can abstract, that there's boilerplate things. They can sense it, they cannot see it, but the abstraction and the system is there, and let's get to it. So for strong normalization, correct me if I'm wrong, but that's how you would define things. You would say that on the unit, a term T of type unit is in a logical predicate if it terminates, right? This is the type index predicate of termination. Okay. And then on such types, on function types, you say, okay, the term has to terminate, but also applying a term S, which is already in the predicate, is also on the predicate. That's the motto. That's basically the characteristic. And then you do the open extension. It looks like this. For any closed substitution, blah, 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 such that every element of the substitution is in the logical predicate, then the result, closing the term, is in the predicate. Okay, so it's tough to reason about those things. It's tough doing the proofs. One of the most annoying parts of such proofs is reasoning about lambda abstractions. Because, okay, you have an open term, you have to prove that the open term is in the open extension of the predicate, so you would be presented with a substitution, and then push the substitution in the lambda abstraction, try to prove the whole term is in the logical predicate, which means that you consider what happens, we have such terms, which then means it will evaluate and support. It's a mess. I don't like it. It's a complex argument. And you know what? With the initial algebra semantics that we're doing, it means we can have any language with variable binding. We can have any semantics, any operators. It can get, for me, unyieldy. We need to systematize this. We need to find more efficient reasoning principles. And let's see how we're going to do it. All right. So this is the topic. I'm going to Using higher-order abstract GSOs, I'm going to abstract the method of logical predicates in two directions. First of all, we're going to abstract over any predicate P, and specifically for the lambda calculus, see how much more efficiently we can reason if we did the thing systematically, and then we'll forget about the operational semantics altogether. We will just consider any old language, any old operational semantics, anywhere, and see, yeah, we're going to get efficient reasoning. Actually, also over here, the efficient reasoning applies, but we'll start with this, with the upper part. All right, let's dissect this logical predicate. I don't like this. I don't like that there is a syntactic part inside the definition of the logical predicate, because maybe my terms don't have application. I don't know. I just don't like it, and you can take it away. Let's, for now, let's just change the notation. Let's write T with label S goes to T prime if T eventually terminates to such a lambda abstraction, and T prime is equal to this substitution thing. All right. So this is what it looks like. This is our new logical predicate. As you see, still defined on closed terms and whatnot. It has the same, basically, I think there is tautology, it's the same thing. But to me, it feels a little bit more systematic, and you can use this to do your proofs. All right. So now, though, what this has exposed is that this is really a parameter of the predicate. We start seeing ways to abstract. So, let's do it like this. Let's define this predicate transformer square, which now depends on this type index predicate P. So on unit, still you define it, P of unit on T, right? And over here, you basically say this. The term has to belong in P. Checks out, right? For instance, it has to terminate. And then, for any term S, or rather, if S applied to T goes to T prime, then for any term S in square P, the resultant is square P. Doesn't it feel sensible? Doesn't it feel that we successfully abstracted away from P? And then I'm going to do something more controversial. So I found the big step, this long step thing, not so fundamental. I consider the small step as a machine, as a guy into operational semantics. I consider the small step operational semantics to be closer to the heart of the machine, it's the way it beats. So let's try to make it this way. Let's try to define it using this, within this small reduction relation. So on unit, it's the same thing, nothing changed. Now, on function types, I keep this the same, the first part, that it has to include the predicate in the definition, right? It has to be baked into. But now I'm saying that if T reduces to T prime, then still T prime is in square P. I'm saying that square P is an invariant. Not only is it an invariant with respect to beta reduction, it's like a greatest such invariant. I'm coinductively defining a logical predicate. And on the function type, largely the same thing. This says here that T is basically a lambda abstraction, right? Right now, right here, right now. So applying to S, the result, T prime, would be in the predicate. So the mode of the logical relations didn't change. For functions, it behaves the way that you'd expect. For not functions, it has to move to a step, and then you can see that if it eventually reaches a function, the key point, the key characteristic will still be existing. I will instantiate now our theorem, our abstract theorem, to prove to you that it's efficient under higher order abstract GSOs to reason about square P. So let P be any predicate on closed terms. And then I'm saying that P is true if all of the following are true. The unit expression is in P, not in square P, in P. Not in the logical relation, basically that unit terminates, say. Okay. The second one, if you have an application TS like this, then if both terms are in the logical predicate, the result is in P, not in square P. You don't prove that the whole term is the logical predicate, only that it is in the parameter, only that, say, they terminate. And then for all lambda abstraction, that P is true. But you're like, that's stupid. That doesn't make sense. So I get no bonus. I get nothing. I just have for all terms. All right. I hear you. Okay. So it's the same thing as before, just slightly more general. And since it was harder to put on paper, that's in the appendix. Okay. So this is how it goes. Things are the same reasoning principles. So now I'm saying that for all lambda abstractions such that, oops, that's a typo. I wanted to just put a dot inside. Anyway, for all lambda abstractions such that the body is in the open extension of the logical predicate, we have just that it is in P. Okay, maybe this sounds still kind of whatever, useless or something. So let's try to prove the strong normalization for STLC using our logical predicates. These are the three things that you have to prove to show that the lambda calculus terminates using our reasoning principles. You have to prove that the unit terminates, all right, pretty clear. You have to prove that the lambda abstraction terminates. It's terminated. You don't have to prove anything. It's already terminated. And the second one, I went like, whoop, whoop, 1, 3, 2. The second one, if both terms are the logical predicate, not open extension, just logical predicate, that the whole thing terminates. All three are super easy. So if you compare this proof, what you need to do, comparing to the classical proof, I think it's much easier. Why, though? Why is this the case? Why do you have this reasoning principle? It's because by the shape of the rules and by the well-behavedness of the lambda calculus, and more abstractly, if you have a dimensional transformation, if your rules are polymorphic, your operational rules are polymorphic with respect to the subterms, there's so much that the language can do. And this translates to the fact that there is a lot of boilerplate code in the proofs which is automatically generated by the naturality, by the shape of the rules themselves. Is it clear at this point why this is simpler or not? Maybe not, yeah. I don't know. So normally you would have to show, maybe you can go back a little bit. Not that much. So recall that, I lost it again. Please recall that normally, to prove that the lambda abstraction is the logical predicate, you follow a long line of reasoning that, the term is in the logical predicate. All right. This is the instantiations of our theorem for the lambda calculus. I will briefly introduce you to the general theorems that we have, and I will talk about this direction here, and this is when I will start being a bit more categorical. So these are the setting of proofs by logical predicates. Let's start translating the setting to category theory. So we have an operational semantics. First, we need a category C. That's going to be our universe of discourse. It can be the category of sets, or all these categories that Benedict and Dima kind of proposed, the pre-shift categories. These are the universe of discourse. So you need an initial algebra, because all the proofs by logical predicates are inductive proofs. You're basically proving that there is no proper subalgebra or an initial algebra. So you need an initial algebra. All right. Otherwise, you cannot do induction. Categorically, or for the higher order abstract-Jesus paradigm, having an operational semantics means that you have a coalgebra, and a kind of a higher order coalgebra. So B here is a bifunctor, and you have a morphism from mu sigma to B mu sigma of mu sigma, which kind of tells you how terms kind of evolve, what their small step operational semantics are, or could be big step, I don't know. So now you're given a type index predicate P mu sigma. Okay, that's monomorphism into mu sigma. That's just easy. Now, what I showed you before, another thing that this theory does is that logical predicate isn't just some empirical kind of thing that somehow it can be created. It is an actual construction. It's a predicate transformer. It's something. You take what you want to prove, you take your predicate, plug it in the transformer, and it's ready. You shouldn't have to define what a logical predicate is, or how these basically concrete relation or predicate liftings work. You should just have it ready for you as a predicate transformer. So I think that's nice. And also, by the way, even I showed you some of coinductive logical predicate, all the other predicates that are in the literature can be given a characterization like this. You just change some of the parameters of your system. And yeah, in the fourth case, you proceed by induction to prove that the open extension of square P holds. And that's a fundamental property. Initial algebras have no proper subalgebras. All right, and in our case, when you expose this machinery, you get efficient generic reasoning principles. I'm going to focus on these three parts here very quickly. I think I'll do a horrible job, but I do hope you learn something out of it. So when I'm saying that we have an operational semantics and a coalgebra, this is what it looks like for untyped system. So I choose this as my bifunctor, and this roughly says that a term may better reduce or behave like a function. So for some term, it's gamma of t is equal to t prime. If it goes one step, it reduces. And then it is, for lambda abstraction, I'm assigning this function here. That's how you should imagine it. This is a well-defined function on terms. And you need something that's known as predicate lifting. You need a way to apply predicates to these structured successors. So if you are presented with this sort of set, which is a disjoint union of identity and, I guess, functions, end of functions, the relation lifting of overline B, P comma Q, is a disjoint union of the set of Q plus the set of functions that map inputs P to outputs in Q. Don't tell me for logical relations people it doesn't trigger you. It doesn't immediately say, oh, bifactorial relation lifting gives me the notions that I'm looking for to reason with predicates or relations. So abstractly, you can define what a relative invariant is. And the relative invariant is, let's say, a P. It's a predicate on the state space of your coalgebra, so a predicate of terms usually, which says the following. If P is an S relative invariant, that means that if a term is in P, its successors are going to be in B bar S comma P. And a logical predicate is precisely a predicate which is relative to itself. Let's translate it for what this means for the lambda calculus. So a predicate P is logical for all terms T if Pt implies what? So if a term is in the predicate, implies what? If T goes to T prime, then P of T prime. If you had something like non-determinism, it's going to look like this. If there exists T, rather, that T goes to T prime, then P of T prime. And then, for all S, if applying S to T goes to T prime and P of S, then P of T prime. And I think in the literature you can find this definition of logicality, right? Let's put it this way, on the relations of predicates. So it checks out. It's a precise and accurate kind of abstraction that captures the notion of logicality. Now, as it turns out, even in the abstract, this construction that I talk about, this square construction, exists for under certain conditions. So recall that B is your behavior functor, right? So it kind of gives you the shape, what kind of system are you dealing with. If this lifting is predicate contractive, just swallow it. I'm going to explain it after this slide, on this slide actually. Then every predicate on the state space of your coalgebra has this magical logical predicate, what you can do proofs on. And this magical logical predicate satisfies all of the properties one wants to do such proofs. So it is included in P. It's smaller in P, so it has P baked into it. It is logical, meaning that you have this nice property of when you apply the already terms inside square P, you're going to get terms in square P. And it's the largest, so it's conductively defined, it is the largest such square P relative invariant, which is what allows you to go through with inductive proofs. This exists in every logical predicate proof out there. It's just hidden. We just dissected it. We just exposed it in the abstract, right? The translation of this thing is that if the lifting is being defined inductively on types, it is sufficient to have predicate contractiveness. So the existence of logical predicates for all intents and purposes, relies on, again, something intuitive, that you define your behaviors inductively on types. Yeah, I haven't given exact categorical details as to how this works, but other people before me did give, right? How, you know, the arrow construction, that assigning types to variables, yeah. Well, what it all boils down to is that all these obscure categorical kind of conditions, they are satisfied under all these reasonable kind of settings. Now, what is that? Okay, you're right. If you have all those things, so if you have now an initial algebra, then operational semantics and logical predicates, what people define as the fundamental property, and this is true also for relations. So the fundamental property is that initial algebras have no possible subalgebras. Thus, if your logical predicate is algebraic invariant, that's how they call it. For relation is congruencies. So if you have congruencies on the predicate level, then square P is isomorphic to mu sigma, your terms. So all mu sigma satisfied square P, all terms satisfy square P. That's the fundamental property. Also P, right? Because square P implies P. And I talked about this very abstract efficient reasoning, and very briefly, if you have high order Jesus laws, that means that previously this operational model over here is induced canonically by this, by the rules are the natural transformations, and they induce the this coalgebra, this operational semantics. Then yeah, instead of doing the common thing, and what people have been doing so far, which is proving that if you have terms whose subholes are in square P, then you don't have to prove that the resulting term is inside square P, but you just have to prove it's in P, which is much simpler. For binding and substitution, some things are not as smooth as, actually, this is true for languages, combinatory logics. You have to change a little bit. Like you have to work on a subclass of Jesus laws that's called lambda laws. But I think the spirit is the same. I'm just throwing it at the rug or something, yeah. Thank you, that's all.
Okay. Thank you, Stelios. Okay, are there questions?
You said the definition of the box is language independent, and
yeah.
I wondered what is the, I think you maybe mentioned somewhat on the last slide, what is the class of languages or operational semantics that you support?
Well, this can be defined even for untyped languages, right? Oh, no, it cannot be defined, of course. Sorry, stupid. Logicality can be defined. So, this is what I'm saying. If you have a coalgebra here, generally, which describes the behavior of terms in such a way that even B itself is inductive on types. Basically, if you have a lifting which follows B, which should follow, then for languages for which their behavior are defined inductively on types, which is true for the lambda calculus, right? Because in the lambda calculus, if you have a term from T1 to T2, then its behavior involves T1, right? Arguments T1 to results in T2. So for such languages and such semantics, so any semantics here, any language here, right? You can define square, this predicate transformer.
But for example, the square really clearly involved the notion of application, I think, or at least
no.
Will the labeling on the arrow or
it just happens that application is predicate constructive. Well, yeah. So, and actual application is syntax. Look at it from the point of behavior.
Okay. More questions? I just wondered, at some point you said something about small step versus big step. Can you repeat? Because it seemed to be the opposite of what I'm thinking.
I believe that the more fundamental, not the more mathematically nice, but the more fundamental transition system is a small step, because this is derived from this.
Yeah, I completely disagree with
Disagree, but let me tell you though this. I'm with you, no problem. Especially in the relation side of this work, if you work with a square on the relation side, using this as your base transition system, the relation becoming of too much fine granularity. your equivalence kind of is really distinguishing many terms. So then you'll be like, let's take this. And you still get efficient reasoning for free.
I mean, to be honest, I had the same, the first slides I could strongly relate to, because when I did my PhD, I used strong normalization proofs. Yeah? And I found them very ugly. But I moved then to more semantic proofs, like normalization by evaluation or a big step normalization, which I wrote a paper about. So yeah, but let's discuss this over beer or something, because I think it's not.
Sure thing. Sure thing.
Okay. Thank you very much.
You're welcome.